Hello everyone, welcome to my channel. Today, we will build a neural network from scratch using PyTorch to solve one of the classic problems in AI, the XOR problem. Whether you are new to neural networks or want to learn PyTorch, this will be an exciting and hands-on tutorial. Let's get started. Before we start coding, let's understand what XOR is. XOR stands for exclusive OR. It's a logical gate that outputs 1 only if exactly one of its inputs is 1. Otherwise, the output is 0. Here's the XOR truth table. XOR is not linearly separable, which means you cannot solve it with a single perceptron. However, if we use a multi-layer perceptron, for example, a neural network with hidden layers, we are able to solve it. A multi-layer perceptron consists of multiple layers of neurons, an input layer, one or more hidden layers, and an output layer. Below is the architecture we will build for XOR. Each neuron in the hidden layer has an active function applied to introduce nonlinearity. In this case, we use ReLU. In the output side, we will use a sigmoid function to classify the output as 0 or 1. Now let's quickly cover the math behind MLPs. The core idea is to compute a weighted sum of the inputs to each neuron. Apply an activation function, and propagate forward through the network. The forward path looks like this. 0 equals to Wx plus b. After the forward pass, we compute the loss, the difference between the predicted output and the actual target. The network then adjusts its weights using backpropagation, which involves computing the gradient of the loss for each weight and updating them using an optimizer. You can carefully watch the dynamic picture in the lower right corner. Now that we understand what the XOR problem is, let's build a neural network using PyTorch. We are in the Colab environment, and first we want to import the libraries. We want to import Torch, torch.neuralNetwork, torch.optimizer, and the matplot library, which is for visualization. We then define our input x and our targets y. This environment has some automatic functions, so it will complete the code automatically, and we only need to change some values. The 4 pairs of inputs and outputs. We can check what's the value of x. And we can also check the shape of x and the shape of y. Next, we will create a simple multi-layer perceptual model. It has 2 input neurons, 2 hidden neurons, and 1 output neuron. We will use the ReLU activation function for the hidden layer and the sigmoid activation function for the output layer to perform binary classification. Let's define the model class. In our case, we also have the activation functions, so we will add the 2 activation functions in our initialization function. Okay, we also have the forward function. This is to connect the input, hidden, and output layers together. Now we have 2 input neurons, 2 hidden neurons, and 1 output neuron. And we also have a ReLU activation function in the hidden layer and another sigmoid function in the output layer. The forward function connects the 3 layers and the 2 activation functions together, and it returns the output value as a return value. Now we will define the loss function and optimizer. For binary classification tasks like XOR, we use binary cross entropy as the loss function and use stochastic gradient descent for optimization. We create a model first and then write the criterion and optimizer. The loss function uses the binary cross entropy, and the optimizer uses stochastic gradient descent (SGD). The learning rate is set as 0.1. Now let's train the model for 10,000 epochs. We will compute the forward path, calculate the loss, backpropagate the gradients, and update the weights for each epoch. In each epoch, we have both forward path and backward path, plus optimization. We will append the loss value to the loss list and print it out. You can see the loss will gradually decrease as the model learns the XOR function. The training is complete now. Let's evaluate the performance of this model. We will feed in the XOR input and see if the network can correctly predict the output. The output should be pretty close to the XOR truth table. We see the accuracy is 75%. Sometimes we can rerun it, restart, and run it again, because the weights will be initialized with random values. Still 75%, then we will try to increase the epochs number. Or sometimes you can change the learning rate value. The loss value is pretty low this time, so it's promising. Okay, 100%. We want to visualize the loss values during the training process. The figure shows that at 2,500 epochs, the loss value has stabilized. So the adjustment of the parameters just now should be due to the initial weight setting, not the number of epochs. Congratulations, you've built a neural network using PyTorch to solve the XOR problem, enhancing your understanding of MLPs. See you next time.